Okay, let's start discussing. So, remember that the way that Dijkstra's works is that we have our graph. It must be weighted. It must be directed in order to run Dijkstra's on it. If you have some other type of graph, you can adapt it, but it's got to get to that state for us to run this wonderfully useful algorithm. It also cannot have any negative edge weights. No negative edge weights in Dijkstra's. We appear to have a graph that meets all of those requirements, so we can run shortest path. We have a start vertex, but notice we don't technically have an end vertex because Dijkstra's is just going to run to generate what we call the shortest path tree, which is the shortest path from the source vertex to all the other vertices. Often you're asking the shortest path from A to, say, B, but in that case, you're just going to run Dijkstra's and you're just going to return as soon as you realize you've hit B. So by default, Dijkstra's just runs to get the shortest path from the start to all the other vertices. The way that we do that is we need to store a little bit of extra information. We need to remember the distance to that given vertex, counting from the original starting vertex, and we need to know what edge do I travel in my journey of shortest path to get to this. So we think of those as back pointers. We need something that's going to store the back pointers, and then we need something that's going to store the distance to. For our implementation reasons, those are going to be maps. Maps with each of the vertices is the key, and then in the back pointers, the edge that you traveled is the value for that one or the distance. So we're going to start by setting the back pointer of A to null. That's where we start. And the distance to of A to 0. I am 0 distance from myself. And then I can start to look out into the graph. And where am I going to look first? Which of these infinite distances am I going to update in my very first step here? Anybody want to raise their hand and share with us how to get this algorithm started? Let's see. I've got some tentative options. All right. Yeah, want to be our hero there? Do you have some suggestions? Yeah. No? Did you raise your hand? Sorry. Yeah. So we're going to start with A. We've marked that as A. Good place to start. Love it. And from A, where do I look? Do I look to A's next in the list? Do I look to those connected to A? A to B? Well, so that's a great place to start, right? We could look at A to B, but we have that pesky little arrow that seems to be pointing not from A to B, but from B to A. So if we're standing on the island that is A, we cannot cross the bridge to go to B from A to B. That's a single directional. So unfortunately, we can't look at that one, but we can see that there are edges that go from A to C and A to D. Those are A's. I like to think of them as next door neighbors. Those are the two places that I can immediately go if I'm starting at A. And we notice that they have weights of 2 and of 1. So what I'm going to do in my list is I'm going to update the rows for C and D with this possible shortest distance. So I'm going to say the distance from A to C is 0 plus the weight of the edge 2. So I get a distance of 2. And then I'm going to mark the back pointer, the previous vertex, as A for C. And then I'm going to do the same for D, and I have a distance of 1. So I've sort of done this like scouting, if you will. I'm like, okay, here are the two places I could go. Which one am I going to select? Where am I going to actually travel to continue iterating in my algorithm? C or D? Ooh, I love it. Okay, let's see. How many people vote for C? How many people vote for D? All right, was that delightful peer pressure? We were all like, we're going to wait for the hands to go up, and we were waiting on D. Me too, team. I play that game all the time. No worries. That's why I ordered it that way. Yes, we're going to pick D because of the current list of possible vertices to go to, that's the shortest distance. Infinity is a very far distance, so those are all out. But it's between kind of 2 and 1 as my possible candidates. One's the shorter distance, so I'm going to select that one. And so it's sort of like I bloop, kind of now I'm like processing D, and now I'm going to expand my purview, and I'm going to look down any edges originating from D and connecting outward to other vertices. And so you can see I've now added in the edge that takes me to B, to E, to G, and to F, which is why you can see I added in fields in those rows. Now I technically have been able to kind of like see every vertex along some path. So you can see, for example, that B, that is the path of the 1 from A to D, and then the 5 from D to B, which gives me a total of 6 and a back pointer of D as one possible route to get to B. And then you can see I did the same things with E, F, and G. I sort of traveled that 1 to D, and then I sort of added on. Now, given this set of options, which vertex am I going to process next? E. E certainly looks like the smallest number in our dis2 category, and that's what we're looking for. Did we do this right? So E is one of them, but then we do have a duplicate. So E, totally correct in that it's 2, but C might beat us out just because it's slightly earlier in the alphabet there. So E or C, both equidistant as far as the next possible moves. Totally correct. So I process the next smallest, in this case C, which had a distance of 2. I update its next pointer. And then you can see that in this case, and that's what the warm-up question was about, I have now brought into my awareness the added edge right here of 1. And so I could see in this added edge here of 2, whereas previously F, the only way I knew how to get to F was to travel the 1 to the D and then the 6 from the D to the F. Now that I've sort of processed C, I've noticed, hey, I could travel both of these 2s and get to F in a shorter amount of distance. So I've updated that what was previously 7 to now be 4. So I wanted to give you an example of how we can go through and replace until we find the shortest possible distance. And so it's like, until we make that decision of like, where am I going to go next? C is the next shortest distance that I can travel. Until I select that thing to process, I can update its distance too until I get to that point. And then once I decide that, then it's sort of like locked in, and that I know is going to be the shortest distance. So F originally started with a distance of 7, because as I sort of moved through the graph, I noticed that I actually can get there in a distance of 4. And then if you see, I can kind of click through these things, and here is my finalized graph. Questions about Dijkstra's? Yes, please.
So when we were at D, wait, what? No, we were at D? Right, wait. Then, but we chose C instead. Is it because it came earlier?
It just came earlier. It was in our queue a little earlier. And so you can see how it says order added to known set. C and E, they were equidistant. We just C came earlier.
Okay, yeah. But other cases, it might be, it might be D or,
It would be, so for example, if E was 2 and C was actually 3,
yeah,
then we would have picked E. But because they were both 2,
yeah,
both could have been, and we just got to C first.
Okay. But I guess when we code, we should specify if there are like 2 nodes with equal distance, we have handle it. I guess we should specify it, or
Yeah, you'll find it just sort of works out this way in the code in terms of how you sort of like iterate through the collection of things. Yeah.
okay.
Yeah. Yeah. Yes, question. So if we are doing a adjacency list graph, we usually don't know unless we iterate over the entire list how many incoming there are. We usually only know how many outgoing there are. And so that's why what I'm going to have is I'm going to have sort of a collection of vertices, and then I have those buckets that store all the vertices I can get to from me. That's usually how the list is going. And so in this case, what would happen is I would start at A, I would go get A's bucket, and I'd be like, where can I get to from A? Both C and D would be in that collection associated with that A's bucket. And then when I eventually selected D, I would then go to D's sort of like key entry in that hash and pull out all its values, and all of D's values would be B, E, G, and F, because those are the ones I can get to from D. So the adjacency list is usually stored in terms of the vertex is the key, and the set of vertices that I can get to from me, meaning the outgoing edges that I can get to, those are the values. Did I answer your question? Yes. So we checked C because originally when we were here, see how C got the weight of 2 right here? We actually sort of exposed C to ourselves earlier than E. And so by the time we get here, we see that E is a distance of 2 as well. But C has already been sort of like known as like a possible distance of 2. So this is still in our options. So the distance, the next shortest distance is going to be 2. C and E have that distance, but C we encountered first. So we processed that one first. But they both follow that like next closest. We just happen to come across that distance of C first. So we process it first. Other clarifying questions? So the final answer is then this sort of filled out table, or the final answer is that shortest path tree, and you can see the little red numbers now. Now I sort of know what is the shortest distance from A to all of the possible vertices. And so now at this point, I could say, hey, what's the shortest path from A to F? What's the shortest path from A to G? What's the shortest path from A to E? All of those things are contained within this answer. If I was only looking for one, if I was like, I don't care about anything except for the shortest path from A to G, then as soon as I sort of like locked in G, I could have returned and bailed out of this algorithm. But this algorithm by default will get the shortest distance from A as a source to all of the vertices in the graph, producing what we call a shortest path tree. And the shortest path tree is really the output of the Dijkstra's algorithm. And it's up to you to use the shortest path tree to decide which vertex do you care about, what's its like shortest distance, and how do I recreate that path by following the back pointers along. So if I did only care about A to G, then I would look it up and I'd say, oh, look, G's distance to is 6, and then G's back pointer is D, D's back pointer is A, boom, my path would be ADG. Yes? Yes. Yeah, edge 2, you can think of that edge as like deciding like that's the path I'm going to take. That's this specific edge that I'm including in this journey. Yes. Any other questions? Okay. Because this sort of ends our conversation about Dijkstra's. I'm going to throw a delightful new algorithm at you today. In fact, 2 versions of doing the same thing, because why not? Because you're going to have to do them for Project 4. Okay, some administrative stuff real quick. We did start grading your midterms. It's going to take us a while to grade your midterms. So thank you for your patience. We definitely spent all of Friday holed up in a room looking over things. And so it's going to take us longer than this week probably to get them back to you. I'll keep you all posted on those. Thanks. Like I said, this is sort of our first time trying to do this format. So we're figuring it out as we go. Reminder that P3 heaps, that is due this Wednesday. Like I said, I think the confusing part is getting started. Please don't wait until Wednesday to get started because office hours will be really uncomfortable for everybody. But I think once you get started, you'll find you can get some momentum. Exercise 4, which is all about graphs and does have a Dijkstra's practice on it. That's going to be due this Friday. And then we will have another exercise 5 going out this Friday on more graphs. Does anybody have any administrative questions at this time? More graph algorithms? Huzzah! Let's do it. Okay. So let's talk about this thing called minimum spanning trees, or MSTs. Okay. Go with me on a journey, if you will. It's the 1920s. It's technically before any type of electronic computer has been created, though Ada Lovelace has written notes as the first computer program. So we're somewhere in the nebulous region between like crank computers and electric computers. It's the 1920s. Your friend at the electric company needs to choose where to build wires to connect all the cities to a central electrical plant. And we want to pick the lowest cost set of lines to lay so that everybody is somehow connected to the electrical grid. And so what you can see here is maybe a abstract drawing of what that collection of cities might look like, where you can see we've got our sort of little power plant kind of nodule down here. And then we've got A, B, C, D, and E representing individual cities. And then the weights on those edges representing the cost for how expensive it would be to lay the electrical wires between the plant and those cities. Maybe some of those places have sheetrock in the ground. Maybe some of those places have water. I don't know. Things that are going to literally materially impact the cost of laying these ground wires. And we want to figure out what's the minimum cost set of edges that will still connect the entire graph together. If you're like, why? Why do we care about this problem? This is literally the problem that invented the thing we're about to talk about. This is a real problem. This is why we invented minimum spanning trees. It literally does come from the 1920s. And the reason I reminded you of that computer thing is because this predates electronic computers, technically. So again, computer science, technically not dependent on physical electronic computers. So this is the MST problem. What do we need? We need a set of edges such that every vertex touches at least one of the edges. The edges, quote, span the graph, i.e. like all of those edges are then connected. We want the minimum weight. And here is my claim to you that the set of edges we pick will never have a cycle. That this will be an acyclic, just like our sort of topo sort, remember? It had to be a directed acyclic graph. The minimum spanning tree is also acyclic. And why is that? And the reason is because the MST, minimum spanning tree, has the exact number of edges to connect all the vertices. If you take away one edge, you will break connectivity, right? Because I want the minimum set. So if I have excess edges that I can take away and these things are still connected, that's not the minimum spanning tree. So if I am guaranteed that one fewer edge will break connectivity, one more edge will probably make a cycle because that will let me get back around to a vertex that's already connected, and that's not what I'm looking for. I do not want any cycles. So that means that the number of edges I am looking for is exactly V minus 1. The number of vertices minus 1. If it helps at all, it's kind of like fence posts, and like the fences between them. If you remember that fence post problem, where the vertices are like the physical posts, you know, and then the like link of fence between them that connects. You always need like post minus 1 number of links between the fence, right? They're the glue that holds the things together. Same kind of idea here. So a minimum spanning tree, given an undirected weighted graph G, find a minimum weight set of edges that you can get away from any vertex to any other in a minimum amount of edges, V minus 1 edges. That's what we're looking for. Let's see. Out of interest, do we think there will always be a unique MST for a given graph? Is this going to be a totally unique deterministic set? Could there be multiple answers to this question? What do we think? Anyone have any ideas on that? Yeah.
Probably no, because it's possible that like two different, like the weights are like the same between like different things.
So there's an interesting thing. So the answer is like probably no, in that like this seems pretty deterministic. We're finding the minimum value, right? And so if we're finding the extreme minimum, the only way there could be a duplicate or some type of other option would be if we had duplicate weights. If we had duplicate weights somehow, maybe we could end up with like 2 different possibilities of MSTs. But if the weights are unique, we are going to have only one possible answer for the MST. Yes, exactly. So, this is confusing. People will always mix up the difference between the shortest path tree and the minimum spanning tree. So I just want to take a moment and remind you that these two things are different. The shortest path tree, and look, you can see I calculated the shortest path tree, doesn't look like the MST because the shortest path tree is about the shortest path from one source to any given vertex. And so you can see, right, like in this context, maybe the shortest path from the factory to D is 8. So I included that edge. That's really important. But in my MST, it's not about source to individual vertices. It's about all of the vertices being connected together. And so in that case, I technically, if I wanted to calculate the distance that it would take me from the factory to D in my MST, I'd have to go down that long path, like here 6, and then here 3, and then here 4. That's a lot longer than 8. That's a length of 13, right? But what I'm minimizing in this case is not the individual distances between 2 vertices, but the total sum of the weights. And so by avoiding that 8 weight edge here, D is still connected thanks to this 4. And the thing that I'm trying to minimize is the sum of 4, 1, 2, 6, and 3, the edges that remain connected across all the vertices. So it can be confusing because technically this is a tree that like looks like it connects all of the vertices, but this is really just a representation of from source to each of these individual terminuses. This is about, hey, as a little ecosystem, what is the minimum amount of sheetrock that the electric company is going to have to bury through in order to get Bertha across the Alaska Way Viaduct or whatever the heck was happening for those 10 years that we were waiting for that. So shortest path from source to target, repeated across all the vertices, minimum spanning tree, minimum summation weight of edges that connect all of the vertices. Everybody's got to be able to connect to the electrical grid. Questions here? Clarifications here? Yeah.
So then, like, it has to be weighted then, right? The minimum spanning tree, and then you can't cheat and say, oh, the shortest path tree would be the minimum spanning tree if it was unweighted.
Correct. Yeah, those two things are separate. Yes. So, and in both of these cases, good thing to reminder, both of these algorithms require weighted graphs. Yes. Okay. So if we're okay with what an MST is, how on earth do we find it? So there's sort of 2 different approaches. You could think vertex by vertex. So you could maintain a tree over a set of vertices and have each vertex remember the cheapest edge that could connect it to the set, and then at each step be like, hey, are you already connected? What's your cheapest vertex? Include you in. Or you could think edge by edge, where you're like, okay, I'm just going to sort the edges. I'm going to find the cheapest edge, and it probably connects 2 vertices. And then I'm going to go find the next cheapest edge and see if it, like, included will connect vertices, and I'll just keep connecting until I get there. This will make more sense as I sort of dig into each of these algorithms. But they both work. They are both different algorithms that have delightful dead white man names on them. The top one, vertex by vertex, is something we call Prim's algorithm. The edge by edge is what we call Kruskal's algorithm. You are going to end up implementing Kruskal's algorithm. I'm going to talk through both of them. I don't think you really need to maintain like a depth of understanding of these two as separate, but I think it's an interesting moment for us to remember how we are doing trade-offs when designing algorithms, which is why we use this as an example to sort of walk through 2 different algorithms that accomplish the same thing. So, how do we do prims? Well, like we sort of did with BFS, we're going to actually start with Dijkstra's Dijkstra's is kind of an adaptation in and of itself of BFS, right? But it's this adaptation that sort of starts from a source vertex and makes intelligent choices about what's the next closest vertex based on distances. And it's doing that greedy algorithm thing where it's just sort of picking like, who's the next closest, right? So that seems quite reasonable a start to build off of Prim's. So let's see if we can sort of map it idea-wise. So just like at Dijkstra's, we're going to start at some source. In this case, it technically doesn't matter where we start for an MST because everything needs to be connected, right? So start at some source, doesn't matter where. Investigate all edges that connect unprocessed vertices, which is exactly what we do in Dijkstra's. Add the lightest edge that grows connectivity to the solution, meaning like touches a vertex we haven't already processed, and then repeat. Sounds really similar. I'm not going to make you do this. So here is a pseudocode for Prim's algorithm. Here is our pseudocode for Dijkstra's algorithm. And if you see here, here is the difference between the two pseudocodes. And if you can see what's happening here, all I'm really doing is instead of building up a cumulative weight from the source to the vertex, right? That's what Dijkstra's is, right? Like I sort of keep that distance 2. I always build up this cumulative, which is like, how far away am I already? Now add this new edge. Instead of that, we don't care about distance from the original vertex. We just want to pick the shortest distance each time. So I sort of let go of that cumulative nature, and I just pick whichever one is the shortest in my possible edges to travel here. And that's it. That's the sort of like stark change there in order to accomplish Prim's. Questions about this little adaptation of the pseudocode, or perhaps about how the Dijkstra pseudocode works? Again, you will be implementing this Dijkstra pseudocode. Yeah. Let's try it out. So let's actually try and walk through this graph where we're going to say start at a source vertex, and then we're going to do this like we're going to accept in new vertices, just picking the next shortest path. So there we go, much prettier. Let's say we start at A. We'll say it's got a distance that is negligible. It's got no best edge. It's processed. So we're starting here at A. Then we can see that connecting A is 2, which takes us to B, 4, which takes us to C, and 7, which takes us to D. So those are our sort of like best edges that would then include these 3 vertices in the set of connected vertices. So right now, I kind of think of it as like, like we're all trying to get connected into one amoeba, and the amoeba is like slowly consuming little vertices to connect into one big blob. And so right now, none of them are connected, and A is the start of our little amoeba. And it's like, oh, do I want to include the B for a cost of 2, the C for a cost of 4, the D for a cost of 7? As you can see here, the animation gave it away, but we're going to pick the 2 because that's like the cheapest cost right away. And now our little collection is going to be A and B. And then I see a bunch of other edges I could possibly include. I'm like, oh, well, the 50 will get us to G, the 6 will get us to E, the 3 will get us to F. And so you can see I updated these 3 vertices are now possible considerations for our inclusion. So if we're going to include, we've already got A and B and this edge between them, which one would we like to maybe include next, you think? Yeah, looks small. There we go. Nice. A good one. And it's connected to B. So now we've got A, B, and F all nicely connected. And then we kind of continue. The 4 is the next one. So that'll be then, let's see, what is that? That's the C, right? So now we have A, C, B, and F all connected. And now we just have to keep going until we find the next smallest way, right? And since we've sort of processed those things, we have discovered some more edges as we've been traveling along. We found smaller weights, which is good because now we have a better edge to pick there, so on and so forth. And then now you can see at the very end of this table, I have the set of edges, the one from A to B, the one from A to C, the one from C to D, the one from C to E, the one from B to F, and the one from B to G. So now all of the vertices A through G are connected, and I have done so utilizing the edges that represent the smallest sum across those edges, the minimum spanning tree. And it looks a lot like Dijkstra's, right? In that same sort of way. We've got our table. We're sort of like looking ahead. We're thinking about what our best choice is. We're making intelligent choices as they sort of come up, so on and so forth. Vertex by vertex. We're kind of crawling through and exposing what's open to us available-wise. Any questions on prims? Like I said, very similar to Dijkstra's. We're just not maintaining the distance from. We're more maintaining what's the cheapest distance to get it included into the set. So that's why we don't care about that distance from right here. We just care what's the next shortest edge that still brings it into the set. Okay. I want to click on these. I think these are actually super helpful. Why would you do that? Oh my gosh, did they really take these away from me? Please don't take this away from me. Oh, okay, wait, hang on. This is really dangerous to do live, but let's see if they just move them. Because gosh darn, I thought those were really, oh no. Oh, I have not double tested this.
Does more than count.
Wow, that was assertive, and I apologize for that. Okay, I'm going to update these links and not subject y'all to them because I don't actually know how good these are yet, unless you can do this really quickly. Are you going to talk? Okay. Yeah. I'm not going to let this, I don't think it needs to talk to us. But there you, this is probably showing it. Yeah. This is probably not exactly as helpful as I wanted to. Gosh darn, these are super, super good YouTube links. Why would you take this away from me, other people? Okay, I'll update these. Anyway, so Prim's algorithm starts vertex to vertex, building off of Dijkstra's, building off of BFS. And so you can kind of see in the visualization that I will eventually maybe find a better version of, where it kind of does these explorations where it sort of starts out here and you kind of grow that amoeba kind of like from the source vertex out. So if it starts in the left-hand corner, it kind of builds almost BFS style, right, where it builds in those sort of rungs and adds things in. If instead we start thinking edge by edge, we actually don't start from like a particular source vertex. We start with a particular edge. And then we just start adding in edges in terms of sorted order. So maybe we add like an edge over here in a graph, an edge over here in a graph, an edge over here in a graph. And then you kind of end up with these separate little islands that get bigger and bigger until all the islands mush into one big amoeba. So instead of like the amoeba like slowly crawling and eating vertices from one source out, we've got a bunch of little islands that eventually kind of like mush together over time. That is a way less satisfying way of giving you those visuals and showing you those YouTube links. But here is Kruskal's, and like I said, this is the one that you are going to implement for P4. So the way that we're going to do this is you kind of start by initializing each vertex to be, we're going to call it a component. So remember how graphs, you don't technically have to have every vertex connected, but we do count a certain set of connected vertices. We call that a component. So we're going to sort of start by saying, hey, every vertex is on its own. Every vertex is connected to nobody, got no neighbors. It's its own individual component. That's where we start. Then we're going to go find all of the edge weights, and we're going to sort them. And then we're going to start. What is the smallest edge weight in the entire graph? And we're going to say it connects two vertices. Every edge connects two vertices by definition. And we're going to ask ourselves, the two edges that it connects, are those in separate components? And so the very first time we do this, every vertex is in its own component, the very smallest edge weight must connect two separate components, and that will be the start of our sort of like bridge building endeavor there. And then we're going to add that, so the shortest edge will get added to the MST as long as it's not like a self loop or something weird. And then we're going to update and we're say, hey, now, thanks to the addition of this edge, U and V are technically connected. Loop again and look at the next smallest edge and ask ourselves, hey, does that now connect in a vertex that is not previously connected to this one? So unless that second edge is a parallel edge, it probably does connect at least to a third one, if not two separate vertices. And then we add those as connected components and we go again. And so that's what this loop is doing. This loop is just looping over every single edge. This if statement is checking, hey, based on the edges I've selected into my MST, are those things connected? We add them, then we update, and we keep looping. I actually think that Kruskal's is probably one of the ones that is kindest to the human brain in terms of like doing it on paper like this. So let's do it together. Let's look at our graph again. Here we've got a graph. Looking at this graph, you can see that what I have done is I have sorted the edges by weight. So you see this AC here, that's referring to this 1. And that 1 is the smallest weight in this entire graph. And right now, we haven't selected any edges to be included. So right now, A and C are in separate components, thanks to this line up here, that initialization. But, okay, apparently I don't have intermediary steps. If I select to include A and C, now these two things are considered connected together. And then I'll go down and I'll look at the next smallest edge, which happens to be this one, 2, which connects C and E. At that moment, C is in a component with A, but E is still off by its lonesome. So I'm still going to pass this if statement because adding in this 2 is going to bring together a set of components that were not previously connected. And in this case, that set of components is the A and C, which are already buddies, and the E is now joining them by selecting in that 2. And then I go to A and B, and that's the 3. And I ask myself, does that include some disconnected component? So now A, C, and E are a single component. They're best buddies. They're all grouped together. Would including this edge to be, does that expand the set of vertices that are connected? Is it going to pass this if statement? By including this 3, am I going to include in a vertex that's not already connected to this component? Yes, I agree. Yes. B, we haven't talked about B yet, so it's still initialized by its lonesome. It's hanging off. It's its own little island. So this little 3 now brings B into the treehouse of friendship with A, C, and E. So now A, C, E, and B are all connected because I've selected this edge, and this edge. So those 3 edges have connected 4 vertices, which makes sense. Remember the fence post problem? We have V minus 1 for that minimum set there. And then I just keep going. So that, what did I just do? I did A and B. Now I look at A and D. That's the next smallest edge, 4. Will this edge, if I select it, will that bring into the club a previously disconnected component? Yes. D is not already part of the buddy group with A, B, C, and E. So I'm going to say yes, and I am going to include that edge. And now A, B, C, D, and E are all connected thanks to the 4 edges I have selected. And then finally, I look at C and D, and I ask myself, hey, this edge 5 between C and D, is that going to expand the connectivity of my edges? Or are C and D already in some way connected together, and thus I don't need this edge? Who wants to vote in C and D? Vote in C and D? Who thinks C to D is duplicate? We don't need that edge. Yes, I agree. Again, I did that tricky thing where I was like, I assume everyone's waiting for everyone's hands. It's fine. C and D are already connected because we picked this one from A to C and we picked this from A to D. So even though they're not directly connected, we can still get to them some way. And if we were to include this 5, then we would have had one of those little cycle things that I said we couldn't have. So we don't need this edge. That is sort of a duplicate if we were to include it. We don't need it to expand connectivity. So actually, we're going to skip along and we're going to go to B to F. And hopefully your brain's like, well, F, that seems like the one we haven't spoken to yet. F's been waiting for somebody to reach out. It's had FOMO. And so now we ask ourselves, if we include this edge from D to F of value 8, is that going to expand connectivity? Is that going to bring in a vertex that is previously not connected somehow? Who wants to vote in the edge to F? Ooh, great question. Oh, you're right. Sorry. This one, my brain was looking at D, but I was looking at this 8. You're right. That's down here. But actually, the B to F, that's that 6 up here. But the same thing sort of applies, right? So now, thank you for catching my brain looking at the wrong thing. Who wants to vote in B to F? Do we want to vote that one in? Yeah, I agree. We're voting in the B to F. That's that 6, which saves us an extra 2 from where my eyes were looking, which is good. And now, all of the vertices are connected. And if I click, here you can see some of the filled out answers. So you can see with the way that Kruskal's works, you kind of end up saying yes in the beginning a lot, right? So you sort the edges and for a little bit, chances are they're not connecting duplicate vertices. It's not until you kind of get deeper in and most things are already connected that you start to maybe have some like, oh, I don't need to include that. They've already been connected. But you can also see maybe a pattern showing that like a lot of the times you kind of say yes to the first edge that somehow comes up connected to a vertex. And so in a lot of the cases, the vertex will be connected via its lightest weight edge, whichever one it is. You know, in that previous example, remember we had G was like, there was only one edge out to G and it was like 50 and really expensive. That's okay. That's got to be part of the MST. If there's only one way to get out to whatever hilltop community that is, if it's through some sheetrock or something, maybe it's expensive, whatever. But you'll find that this sort of pattern comes up with Kruskals that a lot of times you say yes initially a bunch because you're going through those like first sets of connectivity, and then you probably don't say yes until you like the first time you see a vertex. And so for example, all of S's F's edges, blah, 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 are 6, 7, 8, and 9. So we picked the 6, which is its smallest edge anyway. Oh, okay. I was like, maybe it'll throw it. So here is our final answer for our MST for how you run Kruskals. Questions about how this algorithm works? Yes?
They both kind of accomplish the same thing.
Yes.
And so is there one that is preferred in industry? Like, this one's more efficient, this one's easier to understand?
So the question is, which one is preferred in industry? You can imagine that, like, part of the reason I do teach you both is that, like, well, the previous one, kind of we adapted from the Dijkstra's code, really convenient. And maybe you have similar questions to ask and you need to adapt it. So I want to show you that. So that's like Prim's, I feel like, is often used when people are doing something similar or they need to ask questions about it. Maybe you're running Dijkstra's as you go. Like there's sort of stuff in that category. You'll find that Kruskals probably is the one that's used a little bit more commonly because of the thing we're going to learn next, which is a special data structure just to accomplish this exact thing, which actually ends up being a pretty efficient data structure. So the implementation of Kruskals tends to end up being a little bit more efficient than the implementation of Prims. Because there's some tricky stuff we're going to do. Other questions about Kruskals or Prims? So sending us in that direction of, okay, we're going to get asked to do this for our project. Here's our pseudocode, remember? But some of those lines of code were kind of like weird. Is this whole thing about components. And I keep making these jokes about Clubhouse or amoebas or islands or like whatever analogy works in your brain. But we have this idea of sort of like collections. I'm going to call them components. Components are collections of vertices. And there's kind of this idea that like each vertex begins as its own individual component, and then that component kind of grows. And so you can imagine if you have two vertices as separate components, by connecting them, they kind of mush into one bigger component. And so it's sort of like, I don't know, what was previously two components becomes one. These things are actually going to end up being sets. But right now, this idea of like collections of vertices, like we don't really have any good data structures in order to accomplish this so far. Like maybe a set is the closest we have. Like we could make sets of vertices and we could sort of like check if something's contained within this set. If not, make a new set. That's the, like union of two sets. But we're going to end up doing a lot of this sort of like checking inside of things and then unioning sets together. So we're actually going to end up implementing that functionality as its own data structure. And I think that leads me to our next topic, disjoint sets. Disjoint sets is going to be our new data structure that we are going to implement in order to accomplish Kruskal's algorithm. And since we have like a minute, I'm just going to give you a quick idea. Disjoint sets is really just a set of sets. And I'll go back over this. So here we go. This is what a disjoint set is in computer science. It is a set of sets. And then when you union two sets together, they become one larger set still. And so we're going to talk about how you actually implement this data structure and then how you use it in order to accomplish these two sketchy lines of code in the Kruskal's pseudocode. I'll stop it there for today. Thanks so much, everybody. Please come back on Wednesday for our conversation about disjoint sets. Thanks so much.